Okay, so question 1, we have the classic Thomas Young's double slit experiment drawn out like this, and the first thing it asks you to do is on the axis to sketch a graph of how the intensity of the peaks that you see on the screen varies with position. So there are really two important features here. The first is that the peaks have to be equally spaced, so the fringes that you see in the pattern have to be equally spaced, and an important thing in the question was that it used that word monochromatic. Remember, that means that there's a single wavelength, because remember the relationship that you have on your data sheet is that one where W is the spacing of the fringes, and you can see it depends on the wavelength. So if it wasn't monochromatic, you would get a more complicated pattern with different wavelengths having fringes spaced out by different amounts. So based on that, so long as you only have a single wavelength, D and S are fixed, the separation of the slits and the distance to the screen, so the fringes have to be equally spaced. So that's the first thing. And the second thing is that the intensity is greatest in the middle and then drops as you move away, and that's a result of the finite width of the fringes. So you don't have to explain that, but you do have to draw it. So it doesn't matter what the spacing is so long as it's constant. So you just need to draw something a bit like this. So if we have your central tall peak in the middle, and then we come down and then say, right, here's another one here, and then here's the next one here, and then that needs to be symmetrical. So that's got to come down and give a peak here, and then a peak here, sort of like that. Okay, so that's the kind of thing. So the things to look for are that you've got the greatest intensity in the middle, and then it drops off in a symmetrical way to either side, and the peaks have to be equally spaced. Then in B, it first asks you what coherence means. So coherent sources, the important thing is you have to mention two things. First of all, it's that there needs to be a constant phase difference between the two. That phase difference can be 0, so you can have them exactly in phase, but they don't have to be. There just needs to be a constant phase difference, and they need to have the same frequency, so the waves emitted by the two sources need to have the same frequency. Okay, so those are the two things you get the marks for. Constant phase difference and the same frequency. Okay, so then it asks you about the role of this single slit in producing the diffraction pattern. And the story there is that you're only going to get very good coherence between these two sources if the incoming light is relatively coherent, and that's what it's for. So you need to explain how it achieves that. So you don't necessarily have to do the picture, but the picture is quite a good way of explaining what's going on. So remember, you get this kind of effect that light passing through the single slit is diffracted, which means it gets spread out over a range of angles, and so the light arriving at the two slits is going to have a constant phase difference, because in effect it's already been made relatively coherent by this diffraction. So that's the important thing you need to get then. So the single slit diffracts the light arriving from the source, and which means that it spreads out so that the light arriving at the two slits already has a constant or roughly constant phase difference. And that ensures that the interfering waves are coherent. So it's a bit of a waffly question, but I think you need to get in the idea of what the single slit is doing, that it's causing diffraction. And a little sketch like that's quite a good idea to make that point. But the reason that matters is that because the waves arriving here and here derive from the same point source, nearest diameter point source, from that slit, then they'll already have a constant phase difference. So then in part 3 it wants us to explain the origin of the bright and dark fringes. So the key thing in this is that obviously a full explanation is not what it wants here, because it's only 3 marks, so you've got to write it all in a small number of lines in 3 or 4 minutes. But it is important you get the key words in there. And that's often, when you're doing these waffly questions, that's often a thing to remember, is that when they're marking it, they're going to be looking for the key words. So we've already established that these are coherent sources, but it's probably worth saying that again. Okay, then that the slits are coherent sources. Probably not a mark for that because we've already established it, but in general that would be an important thing to establish here when you're explaining this. And then you've got to explain the idea that you get superposition of the diffracted waves from the 2 sources. Okay, so diffraction of waves by the 2 slits leads to superposition. Okay, so that word needs to be in there. And superposition just means that when 2 waves arrive at the same point, you simply add up the displacement of the 2 waves to work out what the resultant will be. And what determines whether you get a bright or dark fringe at the screen is whether, when the waves from the 2 sources arrive there, whether they're in phase or whether they're anti-phase. Right, because if they're in phase, you'll get constructive interference, where the displacements will add up to give you a bigger displacement, so you get a bright fringe, or whether they arrive anti-phase, in which case they'll cancel each other out and you'll get a dark fringe. That's the idea. So you need to get the idea of the word superposition in there, and then you explain that when light from the 2 sources arriving at the same point on the screen is in phase, then you get constructive interference. Okay, and again, it's important to get the words in there, so you've got to explain that it's when they're in phase that you get constructive interference. Which leads to increased displacement compared to the individual waves, which means that you get a bright fringe. Okay, so make sure you got in phase, make sure you got constructive interference, and make sure you got superposition in there. And then I think, just for completeness, it doesn't ask you about the dark fringes, but I think it's just worth, if you've got a little bit of space left, to say, when 2 waves arrive at a position where they're antiphase, then destructive interference decreases the displacement. And that means you get a dark fringe. And that's obviously just saying the opposite of this, but it's getting in the idea then that it's only at certain points that you get the constructive interference. In between, you get these places where there's destructive interference, and that's as a result of the waves being antiphase when they meet. So in C part 1 then we have to calculate the distance between the sources and the screen, and that's going to be your chance then to use this relationship, which is on your data sheet, that W is equal to lambda d over S. And the important thing is to remember which of these parameters is which. So W is the separation between maxima. In other words, it's the width of a fringe. So in other words, that's on the screen. D is the distance between the slits and the screen. And S is the separation of the slits. Okay, so that's the relationship that you're going to use, and so long as you get it right as to which one is which, then it's relatively easy to do this. So it tells you that the slits are separated by 5 times 10 to the minus 5 meters, so that's S, and it tells you that the separation between the centres of two bright fringes, so that's W, is 4 millimeters. So what we've got to do first of all is to rearrange this equation to get an expression for D, because that's what we're trying to find. So we get D is equal to SW over lambda. Okay, so write that down first and then put the numbers in, and obviously it's the usual thing, you've got to be careful to put them in the right units. So they're all lengths, and so they should all be in meters. So lambda is 405 nanometers. Sorry, let's start with S rather. S is 5 times 10 to the minus 5 meters, so that one is already in meters, so we don't have to do anything to that. W is in millimeters, so a millimeter is 10 to the minus 3 meters, so that's 4.00 times 10 to the minus 3. And lambda is in nanometers. Remember, a nanometer is 10 to the minus 9 meters, so that's 405 times 10 to the minus 9. Okay, so you can just put those numbers into your calculator and you get 0.4938 meters, which, if we round it to a sensible 3 significant figures, because that's what the data we put in were, so 0.494 meters goes on your answer line. So it told us that our original 405 nanometer laser was violet, and it's telling us now in part 2 that we're going to replace it with a green laser. So what's important now is that you know the relationship between colours and wavelengths. So remember, as you go through the spectrum, like that, from violet to red, the wavelength is increasing. And indeed the frequency is decreasing, but that's the one that we need to know here. So this was our original, and this is the new laser, so the wavelength is longer. That's the important thing. So if we have a bigger value of lambda, fairly obviously we get a bigger value of W, which means the separation between the maxima is greater. So that's what you say, that lambda is greater for green light, which means that the separation of the fringes, or the separation of the maxima, which is W, is greater. Now the other thing that you should say, which is one of those things that feels so sort of obvious that you might not bother saying it, but it asked you what the difference would be in the pattern. And obviously if you've got a green laser rather than a violet one, then the bright fringes will be green rather than violet. And you might think surely you don't have to say that, but just to be on the safe side, yes you do. So just say that as well, that the fringes, I have trouble writing that word, fringes will be green rather than violet. So fairly obviously, if you know what the geometry of your setup is, in other words, if you know what S and D are, and you can measure W on the screen, you can figure out what lambda is just by rearranging that to get SW over D is equal to lambda. And that's a good experiment to measure the wavelength of a source. But what it's asking you is, if you want to try and make that measurement as accurate as possible, how should you change the apparatus? So the general principle here is that you want the distance you measure on the screen to be as big as possible, because the bigger the distance you measure on the screen, the smaller the error will be, the percentage error in your measurement. So that's the principle. Okay, so you want a bigger distance measured on the screen, because that will give you a smaller percentage error in the distance measurement. So that's the sort of principle here. So how can we achieve that? Well, the first thing that we can do is to increase the distance D, because you can see that if we increase D, we also increase W. And actually that improves accuracy both in our measurement of D and in our measurement of W in terms of percentage uncertainty, because if D is bigger and W is bigger, then the percentage error on D and on W will both be smaller. Okay, so that's the first thing that we can do, is to increase D, which is the source to screen distance. Because that will decrease the percentage error on both D and W. Because obviously it increases, if you've got a bigger value of D, the percentage error on D is smaller, and because of this relationship, if D is bigger, W is bigger, so the percentage error on W will also be smaller. The other thing you can do is to realise that you have a number of bright and dark fringes. So what you want to do is to measure the distance not just between adjacent fringes, so spanned by several, not just two adjacent ones. So you need to make clear how that's going to work. So a little picture is a good way to illustrate that, and say, right, if these are your bright fringes, okay, that's probably too many for that, but if these are your bright fringes, then that's distance is W, so that would be 2W, that would be 3W, that would be 4W. Okay, so you've got to be careful with that. So each of those is W, so that distance is 4W. So e.g. distance between the maxima at the ends of a span of 5 is equal to 4W, and then divide by 4 obviously to find W. But again, you can see the advantage of that is that you're measuring a bigger distance, and so because the absolute error on a distance measurement is always just determined by your measuring instrument, it will be the same absolute error for a big distance as it will be for a small distance, but in percentage terms that's a smaller thing. So that's the first thing you can do, that's the second thing you can do, and there is a third thing, which is to remember that you're used to the idea in physics by now that where possible, rather than try to measure something from a single data point, you try to construct a graph. And you can see in this case that if we plot W as a function of D, then W is directly proportional to D, so we're going to get a straight line like that, and the gradient of the straight line will be lambda over S. Okay, because that's just W is equal to lambda over S times D, so lambda over S is the gradient of the straight line. So in other words, what you do is measure W as a function of D, so in other words vary D, construct that plot, and then find the gradient. And because you know what S is, because you know what the separation of the slits is, you can therefore deduce the value of lambda.